Okay, so thanks to HPC Advisory Council for given me this opportunity to talk about the stuff I'm doing. And today I would like to talk about the Immutable Application Containers. So maybe I should use this dongle. That might work better then. Here we go. So a quick look at the agenda. So first I will introduce Docker to those of you who haven't known about it. And after I will go iteratively to what I've done so far with Docker and log and performance management, which led to my recent work about immutable application containers. So this is me, so you can compare. I have 10 years experience in system operations on various different sites. So I work mostly in the automotive industry, and afterwards I iterated through an R&D position at Bull in Paris. But then I figured that's time to break out of the more the conservative working environment, and I got a job at a small startup in Berlin. And I'm doing the DevOps part there just to get going with startups a little bit. And as a side job, I founded my own little company, so it's a one-man show. It's not that I have hundreds of employees yet, but I'm working on a holistic system management, so I really like to look into log and performance management nowadays, and especially also a focus on containerization, so Docker in particular, and what is the impact of system operations and workloads in HPC in this regard. And I do consultancy in software design and development as a side job. So, Docker in a nutshell, maybe a coconut shell, but I will start with this little slide. Logistics pre-containerization or pre-1960 was a pretty tough job. You had a lot of different goods that you do not want to mix up because the Maserati might interfere with the barrels of oil or the bags of beans or such things. And when you handle it in different environments, it was pretty hard to put it from the boat to a train to a truck in the factories and such, because you had to put the individual things in motion. In the 1960s, someone invented this metal box called container. That was standard container in different sizes, so 2 standards, and there were no mix-up anymore between the goods, so that was a kind of good thing for logistics, and the transactional cost decreases a lot because you can just take the box, put it on a train, put it on a truck, put it on the ship, and off you go. This metrics also spans to system operations. So this is a slide from Docker Inc. Themselves. So you can put different application in your workload into containers and then put it in different working environments. So that's basically what the virtual machines had promised us. Docker tries to deliver it now. And a quick overview or a quick view at the system level. So in traditional virtualization, in both cases, in containerization, we have the server and we have the host system, host kernel. And on top of those, we have the user lands, so which are both of them comprising the operating system, I suppose. In traditional virtualization, we have 2 types of hypervisor. One is on top of the user land, which is type 2, and the hypervisor that encapsulates with the kernel is called type 1 hypervisor. And on top of those hypervisors, we run our normal virtual machines, right? So we have a kernel in each machine, we have software, the user land in each machine, and we have the desired service that we would like to run inside of the machine, also inside of the machine. At Docker, it looks a little bit different. We have only the user land encapsulated within this container, and it directly connects to the host kernel via system calls. And within the container, we only, or hopefully we only run a limited amount of processes, and one of which should be the service we are desired to run. If we want to use InfiniBand within the traditional virtualization, and we saw it in the previous presentation, we detach the InfiniBand device from the host kernel and attach it directly to a guest or virtual machine. or we can use the virtualization technique, but this was the normal way. In Docker, we just have the InfiniBand modules loaded within the kernel of the host system, and each and every container can just use InfiniBand since it uses the same kernel than the host machine. This is now another view on containers or on virtualization, the interface view I call it. We have an application that uses libraries and other programs to connect to other layers underneath, and these applications use as the library abstraction, right? And this connects to a userland, which serves some maybe C libraries or even Python or something to call a system interface or syscall interface and connect to the kernel. And the kernel in the traditional virtualization within the virtual machine uses emulated defs and hypercalls of the hypervisor underneath to connect to the hypervisor. And if we have a hosted version of a hypervisor, we use the userland, so this is the left side. If it's native, we are directly connecting to the kernel, and the hypervisor is type 1. And this actually, at the end, connects to the real system that's underneath the host system. So there's userland and kernel in this orange box. And the host system then connects via the hardware interface to the real hardware. On the containerization side, we just have this application. So there could be two application types, one that talks to a userland, so uses libraries and stuff, or a statically compiled application that uses directly the host kernel. And this connects to, so in the userland part, we are connecting to the host, to the userland, and then we have a kernel interface directly. And this directly connects to the host as the orange box like on the left side. And this we call a container. So either we have only an application that is statically linked, we do not need a userland at all, we can just have an empty file system within the container, and if we need some libraries, we only put the libraries in there that we need to run the application. And this is a very lightweight abstraction without I/O overhead or startup latency, because we do not have to boot a kernel, we do not have to virtualize hardware, and this is pretty fast. For a little, or I scratched the surface of the details, but within the traditional virtualization, it's pretty limited the amount of functions that we have to secure to make a very secure environment for virtualization. So that's why Amazon EC2 or Google Compute Engine, they all use normal traditional virtualization to abstract between different users and different virtual machines, because it's a very limited set of system calls or hypercalls and emulated devices that you have to secure, and it's fairly long-term in use, so it's fair to say that they are fairly secure. On the sorry, now I have to click through it. On the other side, with Docker, or with containers in general, we have a lot of system calls that were initially used directly between the kernel and the userland, which are not secured or not secure to run directly in a containerization context, because you have to use this containerization system calls, this forks and stuff. They have to be adjusted to the security of containers, and this is not done, I think, or not really done for all the different system calls. That's why Google, for instance, says that they will use normal traditional virtualization underneath containers due to the security risk. And they also said that every half a year or every couple of months there is a vulnerability within this system calls inside of containers. So that's why they, for now at least, since this is a quote from last month, they will use foolproof security of normal traditional virtualization. So containers using kernel namespaces to isolate different resources. So if you have one container and you have a second container, they cannot see each other's processes, they cannot see mount points and networks, because containers using the namespacing technology within the Linux kernel. To restrain the allocation or restrict resource allocations, within Linux containers you can use C groups to only allow a certain container, so a group of processes basically, to not run more than this and that amount of I/O operations on a file system, or this and that throughput on a network interface. So you can restrain it very tough due to C groups. Or you can only say that this container should only use core 0, even though he sees all the other cores. So for that you use C groups. Security is a big, tough issue. But there are ways to secure a container. There's SE Linux and Uppermore. But I think most of us, and I include myself, when I run some little tests or even bigger workloads, SE Linux is mostly deactivated. Maybe this will change if we have smaller and smaller and more specialized operating system or distribution like Red Hat Atomic or CoreOS or whatever. There are a lot of them, and emerging. They might be that limited that it's easier to handle such security mechanisms. And I'm sure that Red Hat will come up with a pretty nice and neat way to secure containers on top of Red Hat Atomic. And that goes for the same for the others as well, that they are very focused on this issue, because it's an issue at least in the head of most of the people using it. So we might see some advancements on this regard. And at the ISC, I just received the email. There will be a half-a-day workshop in Frankfurt this summer, where we dive into the talking points of Docker. So in case you want to learn more about Docker and containers, and you want to be able to participate in coffee shop talks or coffee table talks, we try to prevent a deep insight into containers and allow you to explore the goods and bads within it. And we also will touch on, or we will go into how it can be helping in system operations as well as in HPC applications. And I will elaborate on what I'm talking today during this workshop. And there's a second workshop. It's a full day at the ISC Cloud and Big Data Conference in September. So these are 2 Docker workshops. Save the date if you like. And if you save the date and you want to have more, or you want to have topics discussed that are not on the agenda, so please drop me a note, drop me an email. No problem, we will include whatever the customer needs. So the first project I used in this context was Kniep, which was originating in IBPM, which was my bachelor report back in the days. I created an InfiniBand monitoring tool that uses Postgres and RRD tool, which scaled to 12 nodes, and then it crashes, so that was not very very performant. But anyway, I iterated through it a little bit in 2012 and 2013, I think, also, and I use a better approach and used the Graphite framework for performance metrics and Logstash for log metrics, for log events, so that was kind of more performant. And there's one slide showing what was achieved with it. So the metrics is InfiniBand network performance, and the vertical lines are events within InfiniBand. So the red one is the port is down, so then is there some traffic inside of the fabric, and the green one is that a port comes up again, also some traffic with the subnet manager. And that was, I think, a nice step towards the right direction, but since my C code looks very bad, I kind of never touched it again because I haven't much time to do so. And now I recently teamed up with Fabriscale, and they are working on OpenSM, and I provide some performance monitoring tool and some log event tools to enhance the usage of InfiniBand. And tomorrow we will give a talk about the subnet manager from Fabriscale, and at the end I will show some stuff that I contributed to that. So save the time. Tomorrow it's the same spot as this one. When working with InfiniBand and log and performance metrics, I figured that it's nice, but I would like to have an holistic approach towards the HPC stack, the complete HPC stack. So only having yet another tool to drill into InfiniBand problems or InfiniBand metrics, it's not enough. And so I use containers. So the blue boxes are containers, and the red rounded shaped boxes are services running inside of these containers to create a complete HPC stack, so the system side and the workload side within a single node. So I use a laptop, for instance. So I had these 3 containers running a log and event system. I use Elasticsearch and Logstash and Kibana, so all the latest and greatest and fanciest stuff around to play around with it. And I use for performance metrics, I used to use Carbon and Graphite, and now there's another dashboard in town, which is much nicer than Graphite Web, so I use that. And also on the storage side, you can use Carbon, which has a quadrillion of little files floating around, or you can use InfluxDB, which is a Golang NoSQL database for time series data. So I use that for my performance, as a performance engine. And then I add some services that provide me with DNS and service discovery and other stuff that I need to run this little HPC stack. And this I call, I have an HTTP proxy, which proxies the different websites and dashboards to one single entry point. And this I call Kniep monitoring, so that brings everything you need to run a normal or state-of-the-art log stack and performance stack. To make it more holistic, back in the day, so beginning of last year, I also added a compute stack. So I added a Slurm control daemon and some nodes within one laptop to run some MPI benchmarks. But the benchmarks, they were ripped off. All the computation was done. There was just a little weight inside, so a matrix multiplication without the multiplication going on, but the transferring of information back and forth was still in place, so that was kind of nice. And I had, I think, 30 or 32 compute nodes within my little quad-core Lenovo laptop, so that was kind of nice. But I had only this bridge of Docker, so it was not very performant, but to look at the stats and have a little decent set was okay. So the containerized monitoring stack of mine, it comprises of Logstash, which gives this Kibana dashboard and NoSQL database in the back end. I use Grafana, which is a metrics writing dashboard. And if you combine both, then the fun begins. So if you can have a matrix without any context, so this matrix could do anything, right, or could show you anything, you have to know what was going on in this particular time frames or in this particular metric. With Grafana, you can overlay log and performance metrics or information, and this really empowers system operations to have a deep insight and give the context to metrics which you couldn't do before. So imagine if you have network performances with a lot of noise in it and there is an rsync going on and you do not know about this rsync, then you can look at this chart and try to figure out what's going on. But with context from syslog provided as an overlay to metrics, that's basically what really brings the good stuff to the table. And I use Consul, which is a pretty nice service that does some lightweight service discovery and some lightweight health checking like Nagios, but in a sane way and in a nice way with pastel colors, so it's pretty nice to see as well. And it also provides a DNS interface. If you have a service configured in Consul, it will check the service periodically and checks if it's healthy or not and provide a DNS service entry to explore this as well. So that's pretty nice to set up systems which configure themselves. Here's another slide from my Kniep monitor or Kniep terminal thing. That, by the way, is graphite web in the back. So this dashboard, it's a little bit less beautiful than Grafana. But this shows the computation of the matrix multiplication on the top chart, and through Slurm events, you get a context of what's going on. And this is synthetic, so there should be noise, a lot of noise in the network, and this basically only shows the computational iterations. Okay, conclusions about this. There is big headroom to connect the layers. So trace layer errors and events which span over multiple layers. That's basically very nice and a needed view, I think, or a needed thing that for system operations. If you only look at InfiniBand, if you only look at your application logs and metrics, you won't figure out complex problems. But if you look at all of the layers, or most of the layers, important layers, and get a holistic view on the complete stack, then you can do a lot of nice stuff and find out problems that you couldn't figure out before. Especially with the containers on this service or service containers, I think that's a high potential within system operations, because you configure these things once with a fixed port, fixed configuration inside of the container, and then you map different ports to the outside world, and you can run plenty of dashboards with the same configurations that expose different boards. So that's kind of a nice feature. And this could also provide an independent network or environment for training. So if you have a complete stack, or your complete stack of your data center within a box containerized, you could get a new sysadmin and put him in this training environment for 2 weeks, and then he could figure out the biggest pain points in a contained environment. So that's pretty nice for training, but also for integration tests. So if you want to roll out configuration changes or changes in general, you could also first do this in a containerized environment and have some testing done. Do this, and continuous deployment, continuous, you name it. It's basically what you need for this. And to do proof of concepts for new stack components, that's pretty nice as well. So you can throw in another dashboard or throw in another service and try to integrate it into your software stack without touching the actual productive stack. So that's pretty nice. So after working on the service side of HPC, I figured that it would be nice to see as well how MPI workloads running within Docker. So I presented this last year in November in the China workshop of the HPC Advisory Council. And just a quick overview, I got access to an 8-node cluster from the HPC Advisory Council called Venus. It had CentOS 7 installed, dual socket quad-core Xeons with 32 gigabytes and ConnectX-2 network cards. And I put 3 containers on top. So on the right-hand side, you see the picture. So these blue boxes are the containers. I had the native CentOS 7 installation and containerized CentOS 6 and containerized CentOS 7 and Ubuntu 12 environments. And I created 4 partitions. So 1 native partition, spanning over all the native installations, and 3 for CentOS 7, 6, and Ubuntu 12. And there were also multiple OpenMPI versions that I installed in all of this environment, so native and containers as well. I conducted a little MPI benchmark, so this micro benchmark, which is pretty famous to compare the MPI performance. It does an all-to-all between 2 tasks on 2 distinct hosts. And for the native installation, it looked like this. The CentOS 7 userland, or the CentOS 7 container, has similar performance, which is kind of expected because it just is a process or a set of processes that uses the same userland, so there shouldn't be much difference. What was interesting to see is that CentOS 6 was faster than even the native host installation, and this my opinion is due to the more mature CentOS 6 userland. So CentOS 7 in October last year was, or is still not released, so it was pre-alpha or beta, so it was not very mature. And yeah, Ubuntu 12 sucked in this benchmark. I think it's not an HPC distribution, so it was not optimized for this. In a broader overview over multiple MPI versions, so the left-hand side is the distributions MPI version, which in the case of CentOS 7 is 164, and in case of the other two it's 154. And one can see that in the distribution, as shown on the slide before, CentOS 6 was faster than all the others. And when I compiled OpenMPI myself, and with a very basic configuration, I think I just did configure and not much more, it levels out through the different versions of it. But this was not the only benchmark. Actually, this was the main benchmark I did was an HPCG benchmark, which mimics a thermodynamic workflow and more real-world application. And yeah, it's kind of a linpack corrective for more real user workloads. And when I did this on the native installation, I got 4.6 or something gigaflops per second, or gigaflop per second. And I got the same basic result with the CentOS 7 containers. And hence, I said previously, it's the same userland, same kernel, so there couldn't be much difference. When I did this on CentOS 6, it was much faster than the CentOS 7 installation, and as I said before, much mature, so kind of expected as well. And so even Ubuntu 12 was faster, and even faster than CentOS 6 as well. So that is kind of interesting outcome. The GCC of Ubuntu 12 was newer, so maybe that was kind of also beneficial for Ubuntu 12. And here is the overview over all the trusted OpenMPI versions. So yeah, once again, the different versions of OpenMPI and GCC. So Ubuntu 12 was the fastest on the distribution side. And even when I compiled 154 myself, the Ubuntu 12 installation was still faster than the native installation. So that was a nice outcome. So this should have, or has a high potential within the end user application, in my opinion. You build once the container, and then you can ship it around and use it, reuse it on different iterations or workload environments. It abstracts the userland, and so it enables fine-tuning regardless of the bare metal system. So ISV could get a container, create a container, and strip down the libraries and strip down the files within the userland as he needed it to be the most performant. The question I asked myself was, what about the results? Will they be equivalent among different kernels, different operating systems, different bare metal installations? And that's where we come to the topic of the talk, immutable app containers. So as I said, I asked myself, if we bundle up applications, this might be pretty nice, but how about the consistency of the results? So if I run a computation on different boxes and I got different results back, then I don't gain anything. So the question was, how is the consistency? And the container communicates with the host kernel. So also it's not only interesting, or not only the userland of the host box is of interest, but more the kernel version of it. So this is my little test bed. I used this very laptop as a workstation or a laptop for the study. I fetched an old gaming rig of mine as a workstation equivalent, so a normal desktop. I reused the HPC Advisory Council's cluster, which I used last year. And I also run the workloads in AWS. A couple of weeks ago, when I conducted the study, it was C3 X large. And this week, I also fetched the more expensive C4 4X large. With 16 virtual CPUs to have a look at the performance at the current level. As a use case, I used the OpenFOAM tutorial cavity, which is you have 3 solid walls and 1 moving lid and I have a nice video of this, so it's very fast or very short, but you can see what's going on here. We have 3 solid walls and 1 lid that's moving with 1 meter per second above this, and the fluid dynamics within this cavity case is what's rendered. To make it more fun and increase the computational effort, I took this 2D test case and blow it up to 3D, quite big, and stretched the vertices by factor 10. And also I iterate now 50 times in 0.1 milliseconds time steps. And this is a setting I did. I decomposed it into 16 cells because if you change the decomposition, it will change the result. So I use this 16-cell configuration on all of the testbed systems. And I also added some little code fragment that computes at every iteration the average cell pressure within this 3D mesh. And at the end of the computation, I sum up all these average cell pressures, and this is my measure of consistency. So at 50 iterations and 1,000 times 1,000 times 1,000 cells, and the pressure of these cells, an average summed up, is my measurement of consistency. And I'm not an open foam expert, but I reached out to one, and he said that's pretty okay. So I used, as I said, open foam immutable application containers, 3 on, 1 of which was Ubuntu 12 with open foam 2.2.2. Ubuntu 12, same basic system with open foam 2.3.0, and Ubuntu 14 with the newest open foam 2.3.1. I use Ubuntu because it's very easy to install under Ubuntu. Otherwise, OpenFOAM is not that easy. Or for me, it was not easy to install. And I was it worked quite well. The host systems on top of my testbed, once I used boot to Docker, which was back in the days 1.4.0 with the 3.16.7 kernel version. And this week I also conducted the same stuff with CoreOS, the recent version, which uses 3.19 as a kernel. On the workstation I use CentOS 6, Ubuntu 12 and 14 with different versions of the kernel. On the HPC cluster there was 7 with 3.10, and AWS I used Ubuntu 14, the AMI for that, and CoreOS and in different flavors as well. So the result, and I'm pretty fast, so I can slow down a little. The pressure remains the same among all minor releases. So in OpenFOAM 2.2.2, I got 8.6, and you can read the number. So the pressure was consistent over all runs. And for OpenFOAM 2.3.0 and 1, I got also the same pressure among all the different benchmark runs I did, or workload runs I did. The runtime, though, varies a lot. So on my laptop, it took over an hour. The workstation, since I don't game anymore, so it's a pretty old one, was fairly the same. And yeah, you can see the bars. So one node of the HPC cluster with shared memory and InfiniBand was 40 minutes. C3X large, which has 4 virtual CPUs. But the Haswell generation, or the Haswell generation was 20 minutes. With InfiniBand it was faster. And what's pretty nice is that the latest C4 4X large, which uses the latest Xeon and has 16 virtual CPUs, so it was matching my decomposition, by the way, but it was quite fast as well, so 9 minutes. And yeah, that was quite impressive, I think. I wrote a little paper. I wouldn't call it paper because it's not peer-reviewed, but it's a structured documentation. You can download it there, where I describe all the details of my benchmark. Yeah, and I would like to do some more work in this direction. First thing that should be done is the cavity case iterates toward a very deterministic result. So the more effort you put in it, you can only get a finer result, but you won't get totally different results. So what I would like to use is the Carmen Vortex Street use case, or case, which has a very chaotic outcome and is sensitive to random events. So as you can see, there is a flow running through this tube in the middle, or over this tube in the middle, and it's very random where this different in which direction the flow is going. So that would be cool to see if I use this, if the stability and the behavior of this is going to stay with the user land inside of a container. Yeah, this is, I think, the next thing I will do. But I would also like to diversify the use cases. I'm working together with the University of Tübingen to put a pipeline for genomics into Docker as well. So this pipeline comprises of R, and you need some Java, and you need some other libraries that are not very common to install. So by putting it into a Docker container, it should be pretty easy to distribute it and use it among the bioinformatics guys, or the biologists, not even informatics. But if you have good ideas and use cases, I'm open to any use case out there. And another thing that I would like to look at is GPUs and mix. I think the last talk was interesting in this regard because he talked about how this would run on Xen. And if you imagine that you do not have this hypervisor stuff in the middle, but only the host kernel and the user container, then putting this RCUDA workload even in the container could be very nice to see as well. So I will drop you a card. And then that would be nice. And because the question is, if you have this, and I will go into this in the workshop, but just if you have different architectures, since you use the kernel and the hardware is underneath, I think it will only be stable on different architectures or on the same architecture. If you run a CUDA, or if you run a MIG in this version and in that version, that should lead to different results. So this should be interesting to look at. So the results remain stable across multiple hardware versions, operating systems, and so on, kernel versions, and even network technologies, so shared memory or InfiniBand, it was the same. That's pretty encouraging. And this could lead that if you have to legally store your data 20 years or even longer, or you can keep the image. The image is identified by SHA hash, which is, that I will elaborate that on the workshop. So you can keep the image and the input data, and this should be enough because you can recompute this anytime. So anytime in quotes, because there is no long time study. And vendors could be able to fine-tune and certify their different containers. So you can download now. You can download a certified version of Red Hat, or not Red Hat because it's not open, but on CentOS, on Ubuntu, and all the other distributions that are publicly available. You can download their images from Git, from Docker Hub. And in this regard, the software vendor might take the official image from Red Hat and puts his certified software in it, tunes the user land, and then distributes this as a way of packaging up his software. I think this could be a very viable solution. And then and I was a system administrative guy years, so all the bias of which kernel version you use and which library of that sort and that sort, this could all be gone because the user land is encapsulated in this application image, and there is no fuss about which user land is used because you have this SHA hash. You can say, okay, I have this SHA, and you maybe not read the whole thing, but only a subset, and then you can verify that's the same container that was provided by the ISV. So this, I think, should be a cool thing in the future. Yeah, thanks for the attention. There are some credits for the pictures and questions.